Okay, so in here, in this problem, we have to consider three different stages. First, just before the collision, the bullet is flying to the right, but the rod is not moving. Then collision happens, and right after the collision, the bullet is flying back away from the rod. That's the velocity, and the rod starts moving, having some angular velocity, and then eventually the rod stops moving. For this, we have to use the law of conservation of angular momentum, because that's a collision. And for this part, we have to use the law of conservation of mechanical energy, like for the ball on the string. And I've found two issues in your solution. Number one, well, of course, when you write the law of conservation of angular momentum, the angular momentum of a system before the collision should be equal to the angular momentum of a system after the collision. And before the collision, there was only one moving object, the bullet. For a point-like object, for a dot moving at a given velocity relative to a given axis, the angular momentum is given by a cross product. Well, at the instant when the bullet just hits the rod, the velocity and the radius vector are perpendicular to each other, 90 degrees. So it's very easy to calculate the angular momentum of this bullet. It will be equal to mass times the magnitude of r times the speed times, well, excuse me, the direction. Sorry, I hope that's not COVID. The direction could be done by the right-hand rule. This is the velocity, this is the radius vector, and if you will make it move in that direction, that's actually clockwise, counterclockwise direction. Counterclockwise direction makes the product point out of the screen, the thumb at us, and if we use x, y, z axes or unit vectors I, j, k, that should be direction of k, z. And okay, this has to be equal to what? Well, this has to be equal to the momentum after the collision, which is a combination of two, right? After the collision, the bullet flies away. The radius vector is the same, but the velocity points differently. So this will be, well, mass, same r, new speed, times opposite direction. And plus what you write, g. Okay, g is fine. I would write g as the angular momentum of a rod And you just cannot use this expression because this expression only works for a point-like object. That's the issue number one. For the rod, what you could have done is break it down into small parts, and for each part calculate, well, the individual angular momentum, which would have been equal to, you're right, in this instance for the tiny portion of it, mass times radius vector times the velocity of that part. But to calculate total one, you would have to calculate the total sum, which is an integral. And the integration gives you something like this. And because this is a, well, very simple motion, counterclockwise motion, all points of this rod will move with the same angular velocity. It's easier to rewrite it in terms of magnitudes, r times angular velocity, and this is again counterclockwise direction times this, and angular velocity, okay, I'm gonna move on another side. Angular velocity is the same for all, and inside you've got r squared dm. This is the total moment of inertia, I, capital I, and this is how you need to calculate, times k times a unit vector, how you need to calculate the angular momentum of the rod. So your equation relative to z-axis, so we can drop k's, will look like this. Oops. mr vb, okay, m minus, plus omega I. And for I, you have to write, well, big M, the mass of the rod times the length of the rod squared. If it would have been spinning about the middle point, it would be 1/12, but because it spins about the different axes, and look at it at the end, the inertia is, well, shifted by the theorem, parallel axis theorem. So this is how you do that part. But then you have to apply the law of conservation of mechanical energy, and there's another issue here. So for the rod, of course, initial energy will be equal to initial rotational energy plus initial potential energy, and eventually when it stops there will be no kinetic energy, but potential energy will change. But how? And you cannot do this calculation. First of all, you have to look at the motion of a center of mass. The center of mass is changing height. So this is your height. If you would start calculating potential energy from the lowest location of a center of mass, that would be 0, and this would be mgh. But what is h? For that you have to use trigonometry more accurately. So this is center of mass, which means this is 1/2 of the length, and now it rises up to this. So this is again 1/2 of the length, and this is the height you're looking for. This is the angle. And clearly, to calculate the height, you need to do subtraction. 1/2 of the length minus, well, this part, and this will be equal to 1/2 of the length times cosine of theta. So 1/2 times omega squared times 1/3 ml squared will be equal to, sorry, again, confusing symbols. This should be capital M, the mass of the rod. So the mass of the rod, my system is dying, times G times, well, 1 minus cosine theta, and this will be L over 2 as a common factor. So this omega goes to a previous page in here, and that will give you an equation for the angle which you need to solve to get theta. I'm not going to do this mathematics. I know you're good at that. And here, all we need to do is remember the meaning of a unit vector. A unit vector points in the direction of a specific axis, x, y, z. What we know is how dot product works. For example, I times j equals k, and we can see it from the right-hand rule. I times j, well, cross product, so the direction of the motion from I towards j, it gives the thumb k. Well, technically, we should have been using a symbol like this. This symbol represents the direction out of a screen, out of a page, towards us in our eye. So, but this is a three-dimensional representation using a two-dimensional surface. So, if you want to write R, you have to use X and Y axes. So 3, 4, that's your R. And for the velocity, you just need to draw X and Y components of velocity. X component, Y component. X component is positive, Y component actually is negative. So the velocity vector looks like this. If you need to calculate the cross product, which is this cross this, which is this cross this, from R to V, direction is clockwise. Clockwise makes it opposite to K, opposite to Z. So it will point towards negative K, but of course you could get the same from this consideration. If I times J equals K, then you flip switch, J times K equal J times I equals negative K, and that's it. That gives you the direction into the screen, or opposite to Z if the points this way. R times V points the opposite way. These are arrows. And the same, oops. Okay. The same consideration goes for a second part. It just we have to use now not x, y, z, but if I need y and z, so I can flip it. That will be y, that will be z, that will be x, or j, k, I, and again you can say j times k will be equal to I, and k times j will be equal to negative I. So if you want to draw the first vector, that's going to be y, z, y is 5, z is 6, 5, 6, that's r, and v, y, and now v, z, so that is a negative number, negative 8, this is a positive number 4, so this vector represents v. So now we've got r cross v, so r towards v gives, out of the screen, I. Well, again, this is direction provided by j, this direction is provided by k, and right here we get the same, j cross k equals I. So this will be the direction. Well, I could do it this way, v, y, v, z, and this is v, x, yeah, x, y, z. This will be the direction of r cross v for part B. And if you want to calculate the magnitude, it actually now is pretty simple, because angular momentum will be equal to, on one hand, it is equal to cross product, of course. On another hand, it will be equal to magnitudes times the unit vector in the direction. Well, if this is part B, the direction is given by unit vector k. And how do we calculate magnitudes? Well, Pythagorean theorem. Parallax. And same, of course, for this part. Again, your result for part A will be equal to mass times magnitude of the radius vector times speed times, what did we get? Negative k. Same equations for magnitudes, Pythagorean theorem. Well, hope that helps.